Hello my dear students, in this lecture we are going to see one previous year GATE numerical. This question was asked in GATE 2012 for 2 marks. Basically this question is based on finding LMTD with the help of effectiveness. So let us understand the question. The question is water, specific heat of water is given at 80 degrees Celsius, enters a counter flow heat exchanger with a mass flow rate of 0.5 kg per second. Here mass flow rate of water is given. Let us understand first what is counter flow heat exchanger. Now here they have given counter flow heat exchanger. So for counter flow heat exchanger, if I draw temperature distribution, now here let us say it is a counter flow heat exchanger, right? For counter flow heat exchanger, the entry of hot and cold will be from opposite side. Let us say on left side there is an entry of hot fluid. Therefore at entry, let us say temperature of hot fluid is Thi, and as hot fluid is flowing through the heat exchanger, the temperature of hot fluid will decrease, and let us say at exit it will become Tho, right? Tho is exit temperature of hot fluid. Now my dear students, here hot fluid is flowing from left to right. So for counter flow heat exchanger, the cold fluid will flow from right to left. Therefore the entry of cold fluid will be on right side. Tci is the entry temperature of cold fluid, and the exit on left side. Therefore here for cold fluid, exit temperature is Tco, right? And here it is a hot fluid, Thi to Tho hot fluid, and Tci to Tco cold fluid, right? And my dear students, here this left side temperature difference, that is Thi minus Tco, is called delta T1, and right side temperature difference, that is Tho minus Tci, is called delta T2, right? Now again go back to the question. Now about water they have given information. Then here Cp 1 kilojoule per kg Kelvin enters at 30 degrees Celsius. Now this is very important. Now my dear students, here the water at 80 degrees Celsius enters, right? Therefore the entry temperature of water is 80 degrees Celsius, and air at enters at 30 degrees Celsius, right? Therefore the entry temperature of water is 80 degrees Celsius, entry temperature of air is 30 degrees Celsius. Therefore definitely the air is a cold fluid and water is a hot fluid. Therefore here I can say water is hot fluid, and air is cold fluid. Therefore whatever may be the data given for water is for hot fluid, and the data given for air is for cold fluid. Therefore here Cp of water is given. Therefore here we can say the specific heat of water is nothing but Cp of hot fluid is equal to 4.18 kilojoule per kg Kelvin, right? This is the Cp of hot fluid. Then entry temperature of hot fluid, that is Thi is given, Thi, which is nothing but 80 degrees Celsius, right? Then air, specific heat of air is given, therefore it is a Cp of cold fluid. Cp of cold fluid is 1 kilojoule per kg Kelvin. Then enters at 30 degrees Celsius, therefore entry temperature of cold fluid, that is Tci, is given 30 degrees Celsius. Then with mass flow rate of, now here the mass flow rate of air is given, right? So let us write down this mass flow rate. Here mass flow rate of water is also given. Mass flow rate of water is 0.5 kg per second. Therefore here mass flow rate of water is nothing but mass flow rate of hot fluid is equal to 0.5 kg per second, and mass flow rate of air is, that is mass flow rate of air is nothing but cold fluid is equal to 2.09 kg per second. Then if the effectiveness of the heat exchanger is 0.8, the LMTD in degree Celsius is, now here the effectiveness of heat exchanger is given 0.8, and question is to find LMTD. It is log mean temperature difference is equal to in degree Celsius, right? Now my dear students, here for this counter flow heat exchanger, the LMTD value is given as, this LMTD is calculated as LMTD is equal to delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2, right? And my dear students, delta T1 is nothing but Thi minus Tco. So let us write down here delta T1. Therefore delta T1 is nothing but Thi minus Tco, and delta T2 is here Tho minus Tci. Therefore delta T2 is equal to Tho minus Tci, right? Now my dear students, if I want to find LMTD, I have to find these four temperatures, that is inlet temperature of hot fluid, exit temperature of hot fluid, inlet temperature of cold fluid, and exit temperature of cold fluid. These four temperatures are required, but here only inlet temperatures of hot and cold fluid are given. Therefore, exit temperature of cold and exit temperature of hot we have to calculate first, right? And these temperatures we will calculate with the help of effectiveness, right? Now, my dear students, we know that the effectiveness of heat exchanger. Let us find these exit temperature of cold fluid and hot fluid. Therefore, with the help of effectiveness of heat exchanger is nothing but actual heat transfer through the heat exchanger divided by maximum possible heat transfer through the heat exchanger. This is the formula of effectiveness. And my dear students, this actual heat transfer through the heat exchanger is nothing but, if I consider cold fluid, it is EMCP of cold fluid into temperature difference of cold fluid, that is TCO. The temperature difference of cold fluid is TCO minus TCI. This should be the actual heat transfer through the heat exchanger. If I consider hot fluid, then it will become EMCP of hot fluid into temperature difference of hot fluid, that is THI minus THO. This will be the actual heat transfer through the heat exchanger. And the maximum possible through the heat exchanger is nothing but, my dear students, it is EMCP minimum, that is EMCP small, out of these cold and hot fluid, whichever may be the smaller, that smaller value we have to use EMCP small into delta T max, maximum temperature difference in the complete heat exchanger. The maximum difference will be the hot temperature inlet temperature minus hot cold fluid inlet temperature, that is THI minus TCI will be the maximum temperature difference over here, right? So, my dear students, let us find this actual heat transfer rate and maximum possible heat transfer rate, right? And let us find this effectiveness. Effectiveness is given, right? So, to calculate this maximum possible heat transfer, we have to calculate the EMCP small. So, let us find here EMCP values, because EMCP is given for both. So, let us find here for hot fluid and cold fluid. If I take EMCP of hot fluid, then it is equal to, for hot fluid, mass is 0.5 and CP is 4.18. Therefore, it is 0.5 into 4.18, which is equal to 2.09. Right? This will be the EMCP. Right? Therefore, again let us calculate for cold fluid. Therefore, EMCP of cold will be equal to, see what will be the unit here, the mass in kg and Cp in kilojoule per kg Kelvin. Therefore, it will be having unit kg into kilojoule per kg Kelvin. Therefore, kg will get cancelled. Unit will be kilojoule per Kelvin. Right. Again, EMCP of cold. The mass of cold is 2.09 and Cp is 1. Therefore, it will become 2.09 into 1, which is equal to 2.09 kilojoule per Kelvin. Now, my dear students, here we got one result. EMCP of hot is equal to EMCP of cold. Therefore, my dear students, it is a special case here, right? If the heat capacity, EMCP is nothing but heat capacity. If heat capacity of hot fluid is equal to heat capacity of cold fluid, that means for both it is having minimum. It is for both EMCP is small as well as for both EMCP is large, right? For both EMCP is maximum as well as minimum. Therefore, EMCP you can use here for EMCP small, for hot also, for cold also, right? Now let us check this formula. Now, my dear students, therefore here with the help of this effectiveness formula, therefore effectiveness of heat exchanger becomes Q actual divided by Q maximum possible. Q maximum possible is equal to, for Q actual, if I write EMCP of cold, TCO minus TCI, right? For Q actual, EMCP of cold, TCO minus TCI. Then in denominator, let us use for maximum possible, for Q maximum, let us use this EMCP small as EMCP of cold, because here EMCP of cold as well as EMCP of hot is minimum. Both are equal means both are minimum as well as both are maximum. Therefore, let us use here EMCP of cold into the maximum temperature difference. Maximum temperature difference is nothing but, here maximum temperature difference is nothing but, here maximum temperature minus minimum temperature. Maximum temperature is THI minus minimum temperature is TCI, right? Is equal to, now again for this Q actual, if I use EMCP of hot, THI minus THO, right? Therefore, let us write here EMCP of hot into THI minus THO divided by, now let us write here for EMCP small, let us write EMCP hot. Therefore, it will become EMCP of hot into THI minus TCI, that is maximum temperature difference. Therefore, my dear students, here in this formula, EMCP of cold will get cancelled, EMCP of hot will get cancelled. Therefore, the resulting expression for effectiveness will become effectiveness is equal to here TCO will be there, TCO minus TCI, make a correction. Therefore, TCO minus TCI, that is temperature difference of cold fluid, they have a maximum temperature difference, that is THI minus TCI, is also equal to temperature difference of hot fluid, that is THI minus THO, they have a maximum temperature difference, that is THI minus TCI, right? Now let us put the values in this equation. Effectiveness is given 0.8, you will find here effectiveness is given 0.8, TCO and THO is unknown, rest other temperatures are known, therefore is equal to TCO minus TCI is given. Here you will find TCI is 30 degrees Celsius. However, THI is also given 80 minus 30, which is again equal to THI is nothing but 80, right? THI is also given 80 minus THO is unknown, divided by 80 minus 30. Now, my dear students, in this equation, only TCO and THO are unknown. Therefore, if I equate this first equation, then I will get TCO, right? And if I equate second equation, then I will get THO. So let us find here TCO and THO. So my dear students, here I will get TCO is equal to 70 degrees Celsius and THO is equal to 40 degrees Celsius. It is a simple calculation. Let us calculate them, right? Now, very important step, my dear students. As here EMCP of hot is equal to EMCP of cold, then it is a special case of counterflow heat exchanger. Is a special case of counterflow heat exchanger. Therefore, for such type of case, that is, if EMCP product of hot and cold is same, then for counterflow heat exchanger, the LMTD is nothing but delta T1 is equal to delta T2. Right? We know that. Therefore, for this special case, LMTD, log mean temperature difference of counterflow heat exchanger, is equal to delta T1 or equal to delta T2. Right? Any difference. Therefore, LMTD is nothing but THI minus TCO. Now, THI is nothing but 80. THI, delta T1 is THI minus TCO. TCO is 70, which is nothing but 10, right? Which is nothing but 10 degrees Celsius. Again, if I use delta T2 is THO minus TCI, right? Delta T1 is THI minus TCO, and delta T2 is THO minus TCI. Now here THO is 40 and TCI is 30. Therefore 40 minus 30 again 10. Therefore, my dear students, for this question, LMTD is 40 minus 10 or 80 minus 70, which is nothing but 10 degrees Celsius. Therefore, if you look at the options, here I have erased the question, but if you go back to the question and if you look at the options, you will find option C will be the correct choice. Thank you, dear students. In next lecture, we will see one more numerical on this topic, which was asked in previous year GATE examination.